Okay, so tonight we're going to talk about total quality management, and it will actually be more than that. It will include some of the statistical process control types of things from Chapter 6. So this will include material from both Chapters 5 and 6, mostly as a review. I will allow time at the end for questions, or if you have something pressing at the time, I will try to watch chat a little bit and be able to answer some, but most of it will be at the end. I would suggest you mute yourselves unless there's something specific you want to ask throughout the presentation. I did a PowerPoint presentation. I'm going to share my screen with you and show that to you and talk through it. And again, let me know what questions you have, and I'll allow more time at the end. Okay. So let me see about sharing my screen with you. All right. Are you seeing my opening screen? Everything good there? Okay, terrific. So let's go ahead and get this going. So the first question when we're talking about quality is, what is quality? And obviously that's a good question, but it depends on who you are, what you're looking at, and whether you're an internal or an external customer. So when we define it, there's a lot of different ways to define quality. An internal customer, I know that many of you work, most of you work. So an internal customer would be somebody within your organization that you're passing information along to, or a spreadsheet along to, or something of that type. So let's say you were in accounting and you had some internal figures you had to share with somebody else within the organization to make a decision. They would be your internal customer. We also have external customers. They would be people outside our organization that we're supplying a product or a service to. And so quality depends a lot. The definition depends a lot. Are you an internal customer? Are you an external customer? Is it a product? Is it a service? So I know that's not very comforting to think, well, how do I know which definition they're talking about? But again, even if we're an internal or external customer, our view of quality, our definition of quality may be totally different than somebody else's. And I'll come back to that in a couple minutes. So here are some typical definitions of quality: conformance to specifications. How well does a product or service meet the targets and tolerances defined by its designers? Fitness for use evaluates the performance for its intended use. So in other words, if you have something, let's say you have a chair that can hold up to 200 pounds and you set 300 pounds on it and it breaks, well, that wasn't in its intended use. Value for price paid, evaluation of usefulness versus how much you pay for it. We all have different views on the value of an item. We could all buy the same item, and some of us would think we paid too much. Some of us would think we got a bargain. So again, that varies. Support services, think about when you buy a computer or something of that type. Are there after purchase support services? The same way with your car. And then there's psychological, and a lot of times we don't think about this, but psychological includes things such as ambiance, prestige, is it a friendly staff, those types of things. And again, I'll mention this as we go along, okay? So the other thing that we need to look at when we look at quality is, excuse me, manufacturing versus service quality. So let's just pick things that we're familiar with. For example, manufacturing. Let's pick a car. Most of us have ridden in a car, driven a car. I'm sure many of us own cars. And for a service, let's talk about a restaurant. I think most of us have probably gone to a restaurant. So when we look at quality in each of these areas, they vary. They're different. So in manufacturing, for a car, does it conform to what the manufacturer says it should? Does it get 25 miles to the gallon? Performance, how does it perform? Does it get the horsepower that it should get? Reliability, is the car breaking down all the time, or is it reliable? We don't have to take it into the service shop that often. Features, does it have air conditioning? Let's hope so, especially this summer since it's been so darn hot. What kind of wheels or tires does it have on it? Durability, what is the life of the car? Is it durable? Does it last a long time, or do you have to replace it in 5 years? And serviceability, how easy is it to have serviced? Those are just some ways that we might measure or look at quality in manufacturing. And again, if I ask each one of you, how would you define the quality of a car? What's most important to you? You may pick something totally different than I would pick. Something that's really important is safety. And so again, the way that we look at quality in a car would vary among us. And the same with a restaurant. When we're talking about a restaurant, we're talking about intangible factors. Let's say this isn't quite intangible, but let's say, where is it located? How is the parking? Is it easily accessible? Consistency. Well, is the food consistent and good? Or one time you get a good meal and the next time you don't? Responsiveness. If you call to make a reservation, are they responsive to you? How well do they serve you while you're there? And is the wait staff courteous and friendly to you, or the host or hostess? Promptness and timeliness. Do you have to wait a half an hour for your meal, 45 minutes, an hour for your meal? That type of thing. And atmosphere. Okay, let's face it. McDonald's has a totally different atmosphere than Ruth Chris Steakhouse. That makes a difference on what we think about the quality of the restaurant. And again, we were talking about ambiance. What kind of lighting? What kind of music? What kind of seating does it have? So those all go into how we view the quality of a restaurant. And I always find a restaurant a good example because we may all go in, we may all purchase the same meal, and our view of the quality would be different, again, among each one of us. So again, the point is that we measure a manufactured goods quality differently than we do a service items quality. The other thing is that quality is much easier to measure in a manufactured good than it is in a service. Again, our view of a nicely cooked steak may all be different. In a car, does it get 25 miles to the gallon? Yes or no? So, all right, let's move on. I'm going to have a little knowledge check here for you. I'm going to give you a couple minutes to think about this. Well, maybe not a couple minutes, but a little bit of time. Which of the following quality gurus' main contribution was it stressed management's responsibility for quality and developed 14 points to guide companies in quality improvement? Was that Ishikawa, Duran, Crosby, Taguchi, or Deming? So think about that. And who do you think that was? You can put your answer in chat. I can't see it right now, unfortunately, but I can go back and look at it after this session is over. So let's see who it was. W. Edwards Deming philosophy on quality was that it's management's responsibility for quality, and he developed the 14 points to guide companies in quality improvement. All of these people have added to developing our quality philosophy on things and our quality knowledge. Ishikawa did the fishbone diagram, which you should see in your book. Duran had views on the management's input and those types of things as well. He was he defined quality as fitness for use and developed the concept of cost of quality. Philip Crosby was that quality is free, and Taguchi focused on product design quality and developed the Taguchi loss function. I like math. I studied Taguchi's his view on quality, and I have to say, unless you're an engineer, I don't recommend that you try to replicate what he does with quality. But he does have important things on producing things for society. Society adds to the quality or determines the quality. All right, let's go to the next knowledge check. If I can get this to go forward, there we go. Which of the following is not a basic concept of TQM or total quality management? A, quality is free. B, employee empowerment. C, continuous improvement. D, product design. Or E, customer focus. There's 7 basic concepts of TQM. 4 of these are true concepts of TQM. 1 is not. Which one is that? All right, let's take a look at which one is not a basic concept of TQM. Quality is free. Again, that was Philip Crosby that had that concept that quality is free. I should say Crosby, sorry about that. I mispronounced his name. So quality is free is not a basic concept of TQM. The next knowledge check, the Yum restaurant decided to send all of their wait staff to TQM training. Which cost of quality are they incurring? A, internal failure cost. B, prevention cost. C, production cost. E, external failure cost. Or E, appraisal costs. There's 4 costs of quality, which you should study in your text. One of these is not a cost of quality. Well, actually, what I want to know is which one is the cost of quality when they send their wait staff to training. But one of these is not a cost of quality. All right, let's take a look. Prevention cost is not the cost of quality of TQM training. Prevention costs have to do with training, education, process, and product design. Okay, so we are preventing a defect or a quality problem from ever occurring before it does, before we produce a product or provide the service. So again, prevention cost includes training, education, process, and product design. Okay, let's see what comes next. Total quality management is very important across the organization. I taught operations management for a long time, and one of the things that I told my students in operations management is that quality is one of the topics in this course that everybody encounters. Whether you work in a for-profit organization, a nonprofit organization, you are self-employed, you work for another company, quality's there and everything that happens within that organization. So marketing has to find out what the voice of the customer is. I always think of quality as meeting customer requirements. Marketing is the outward facing organization that's going to find that out and bring it back to the organization so we can work on developing better quality and meeting the customer requirements. Finance, we have to pay for quality, invest in it, you know, whether it's prevention costs, those types of things. So finance gets involved in looking at trade-offs in terms of our processes, our products, the service we provide, and what we can afford to do. Accounting is going to keep track of whether our investments have been beneficial to our organization. They may be involved in cost benefit analysis, those types of things. Engineering is going to help us design our product and our process. Even when we're a service organization, we have processes, and engineering may be designed in developing those for us. Human resources has to take account of our inventory of quality talent within our organization. What quality talent do we have? What training do we need in the area of quality? And when we hire, what type of background in quality do the people that we hire already have? Information systems, well, we measure a lot of things. So information systems has to help us determine what systems we use to measure the quality within our organization. So quality cuts across the organization in every way. All right, we're getting into some of the more deeper, that's bad grammar, sorry about that. We're getting into some of the deeper concepts in chapter 6. So let's talk a little bit about statistical quality control, and we're going to start with sources of variation. We have common or random variation. Random causes cannot be identified, and they're unavoidable. We really don't have any control over those. So I use different examples to illustrate this. Let's say that you get up every morning and you make coffee, and you do it the same way every day. Now, when you think about it, does it take you the exact same amount of time every day when you make coffee? Probably not. Some days you're faster at it, some days you're slower at it. Why? We don't know for sure. Maybe we're more tired, maybe we're distracted. But those are random causes that occur, just variability in life. So that would be a random variation or a common variation. On the other hand, we have assignable variation. These causes can be identified, and we want to eliminate these causes because these are the things in our life that create quality issues. All right, so we want to eliminate those causes. So let's say we're making coffee and the dog comes over to you. I have a dog, so I use dog examples a lot. The dog comes over to you and in the middle of your coffee making and wants to go out. All right, we have an assignable cause for why it took you longer this morning to make coffee, because the dog came and interrupted you. How can we eliminate the cause? Maybe we take the dog out before we start making coffee. Maybe we need to look up how much coffee to use because we're new at making coffee, or we've changed brands, or something different has happened. If we're new at making it, or we have a new coffee maker, we may have to train ourselves on how to make coffee, so it may take us longer. Or maybe the coffee maker won't start. Well, that's a very obvious assignable cause. So what's our solution? Well, we go probably buy a new coffee maker. I don't see myself tearing my coffee maker apart to try to fix it, but that would be an assignable cause, and we want to eliminate that problem so it doesn't take us 2 days to make a pot of coffee. So when we look at quality, quality issues are created by variation. If you studied statistics at all, variability is not a good thing. We want to eliminate as much variability as possible and try to determine where that variability is coming from and try to improve that. All right. So one of the things that many companies use within their organization is called a control chart. So it's very common, and control charts are used both in manufacturing and service sector. I was fortunate enough to teach in Australia for a while, and one of the gentlemen that I visited and toured his facility had laboratory where they analyze blood. He used control charts, extensively, and had them posted everywhere throughout the lab and the offices. So I'm just pointing out that control charts are used everywhere. So we can divide the things that we measure into two categories: variables and attributes. We're going to start with variables. Variables are the things like length, weight, temperature, those types of things. It's a real number. In other words, the precision depends on how many decimal places we go out, okay? So there's two control charts that we can develop for variables: an X-bar or a mean chart, and a range chart. So the X-bar chart, and these actually are used in conjunction with each other. It's not typically either or, it's both of them we use together. So an X-bar chart is used to monitor changes or shifts in the mean or the average value of a process. So let's say that we make boxed cereal, and I don't really eat much cereal, so I don't know how much a box of cereal weighs. Let's say it weighs 12 ounces. So our cereal boxes should on average weigh 12 ounces. And we're going to chart that. We're going to take samples. Maybe we take 10 boxes of cereal off the line every hour. And we're going to take the average, and we're going to chart those averages throughout the day. And we're going to see how much each of those samples weighs on average to see how close we're hitting 12 ounces. The range is used to measure the dispersion or the variability of the process. So in case you don't remember, the range is the largest value minus the smallest value. And we're going to do that with those 10 boxes of cereal. So let's say one of them's 12.5 ounces. That says the range is a half an ounce. And we'll do that for those 10, and then we'll plot the average range. What we're looking for is whether our process is in control. And again, I don't know how much statistical background you have, but for those that are stat nerds, this is all based on the normal probability distribution. So typically our control charts are plus or minus 3 standard deviations. We want our cereal weight to fall within those 3 standard deviations, our upper and lower control limit. So here's an example of control charts. The X-bar chart and the range chart will both look similar to this. We have an upper control limit, a lower control limit, and the target. For the X-bar chart, our target would be 12 ounces. For the range chart, our target would be 0 because we would like to have 0 variability. We would like all of our cereal boxes to weigh 12 ounces. So this is the plot across time. And what you see on the left-hand side is what we want our plot to look like. We want as many observations above as below. We want all of our observations within our control limits. That says our process is in control. We're producing good product. We don't have quality problems or defects. The chart on the right creates a problem. It's an unstable situation. So if you look towards the middle, you'll see that we have a point out of control, the point that is above the control limit. That creates a quality problem or a defect, and we need to find an assignable cause for that defect. When we're out of control, there is an assignable cause. Maybe the machine filling our boxes went out of calibration and we have to go back and reset it so it's calibrated. When we look at the chart again on the left, that is showing us random or common variation. So that's what we would see when we see random or common variation. The chart on the right, again, the ones in red were moving out of control. We went out of control. At the end of that chart, you'll see those are highlighted in red, but they're not out of the control limit. These are problematic because we see a downward trend. All right. You're buying cereal. Your cereal box does not have 12 ounces in it. Now, there's going to be trade-offs throughout. Sometimes you're going to buy cereal, it's going to be over 12 ounces, sometimes less than 12 ounces. But this process is moving towards being out of control on the lower limit. That's going to displease the purchasers of cereal boxes. So we need to try and get this process back in control by back into just random variation. We need to look for what an assignable cause is and be proactive and get a grip on it before it goes out of control and we create defects. So again, these charts are very, very useful. Companies use them all the time because it helps prevent defects and it helps them save money. We also have control charts for attributes, all right? Control chart for attributes or proportions or counts, they're an integer number. So let's say we produce shirts. Each shirt should have 5 buttons on it. We're going to look at the shirt. Does it have 5 buttons? Yes, no, good, bad, fail, pass. Those are attributes, okay? So a P chart is a proportion chart. It's used to measure the proportion defective in a sample. So let's say that we work at a bank, we have bank statements. We're going to count the number of bank statements in our sample, and we're going to calculate that proportion, and we're going to plot that on a control chart that looks very similar to the ones that we just looked. So let's say that our sample size is 100 bank statements. We look through 100, we find 5 that have errors. So the proportion is 0.05, 5 out of 100 bank statements. We look at them tomorrow. We take a sample of 100 and we have 10. So now we have 0.1 as our proportion. And again, number of shirts missing a button. If we took a sample of 20 and we counted 2, then we could calculate the proportion and plot those. The C chart is used to monitor the number of defects per unit. Now, the key here is per unit. So for example, let's say we make textiles. We can count the number of defects in a yard of textiles, and then we can develop a C chart. Likewise, let's say that we make sheets of plywood. We can count the number of knots in a piece of plywood. That is our unit, and we can chart those as well. So a P chart and a C chart also look very similar to what we saw before with upper lower control limits and targets. Knowledge check. 6 Sigma quality implies how many average defects per minute? 6, 2600, 3 Sigma, 3.4, or 6 Sigma. Give you a minute to think about that. 3.4 is the correct answer for this question. So 3.4 defects per million. That's 6 Sigma. Motorola created 6 Sigma. Many, many companies have followed in their wake and utilized 6 Sigma. Next, knowledge check. In 6 Sigma programs, individuals who have extensive training in the use of technical tools and are responsible for carrying out the implementation of 6 Sigma are A, green belts, B, blue belts, C, black belts, D, white belts, or E, red belts. So think about that. All right, let's take a look at what the correct answer is. Black belts. Black belts are one of the top levels that you can be certified in Six Sigma, and there's even different levels within black belt. All right, next knowledge check. What process capability index value implies that the process exceeds minimal capability? A, 6 sigma. B, 0. C, it equals 1. D, 1. E, greater than 1. All right, let's see what the correct answer is. Greater than 1. Now, process capability can be a little confusing, and I know we've met our 7:30 time limit, but I wanted to say one thing about process capability, and then I'll open it for questions. Process capability, you're just looking at whether the process you are using meets the acceptable tolerances. So I had used this example before. Let's say that we produce the vaccine for measles, mumps, rubella, and the target milliliter dosage is 0.5. But let's say that the vaccine is effective as long as we only have an allowable tolerance of 0.0025 milliliters. So we have an upper and lower limit. So that's what the manufacturer has set and said, okay, this vaccine is acceptable as long as we're in those limits. So now we're going to measure our process. And so let's look at the process that has 0.0005 variation in manufacturing. When we look at process capability, again, plus or minus 3 standard deviations. If we look at the plot in the middle, our vaccine is very effective. Okay, we're well within, our process is very capable of producing this vaccine within the limits. That would give us a process capability index greater than 1. If it meets the limits exactly, our process capability index is 1. If we look at the third diagram, we have variation in manufacturing of 0.001, and we go plus or minus 3 standard deviations. When we look at that and compare it to the top diagram, we are outside the limits. That says that our vaccine could be incapable of protecting our patients because we may have some that are below 0.4975 milliliters or some that are above 0.503 milliliters, and the ones below would be incapable of protecting. The ones above could overdose our patients. Our process capability index would be less than 1. This is a bad thing. So what we're trying to do is look at our process. Is it capable of meeting the standards that have been set out? And if it is, the capability index will be 1 or greater than 1. If it's not, it's going to be less than 1, and it is going to create problems. I'm going to stop there for now, so let me stop sharing my screen. Well, let me show you that. We're going to go to questions. So let me stop sharing. Okay. So I hope that you found that useful. I hope it answered some questions for you. Does anybody have any questions that I could answer for you at this time?